Hello, my name is David Waltzman, and I'm a Senior Simulation Product Specialist with GoEngineer. Today I'm going to be talking to you about plastic design to prototype. The big picture of what we'll be looking at today is this miter saw. Within that saw, we'll be taking a detailed view at this handle. Right, so this is how the user interfaces with the machine, and we need to make sure that that happens properly, otherwise we get accidents like this. I don't know about you, but I don't want to end up in the hospital just because of my handle not being designed correctly. So the goal today is to minimize the weight of the handle while maintaining a factor of safety greater than 5. We hope to pick up some cost savings along the way, as well as create a more comfortable grip and ensure the manufacturability of the product. So we'll start off with our initial design, show what it looks like to send that digital information to a 3D printer. And then from there, we'll optimize for strength and comfort and finish off by verifying the manufacturability of our part. To begin, we're starting off with a shell thickness of 2.5 millimeters. Right? So to create our mold, we're going to keep everything parametric and updatable in our feature tree by using the mold tools inside of SOLIDWORKS. So here's the bottom and the top half. So from here, let's fire up SOLIDWORKS simulation. First step is to define our material type. In this case, we'll be dealing with a nylon. From there, we're going to simulate the other half of the handle being there by using our symmetry condition. Since we're breaking up everything into small triangles, the less triangles we have to analyze, the faster the analysis. Now we have to say how this is held in 3D space. So to be realistic, we're fixing both ends of our handle. From there, we'll be squeezing this with our hands. So I'm applying a force that's normal to the surface of our grip. The last touch before running it is creating all those triangles I mentioned earlier. We get many results from running a simulation. One of the ones that's more important to us is the von Mises stress. This is used commonly in finite element analysis because it gives the stress at a point and doesn't depend on direction. So we compare this with the yield strength of our material to see how our factor of safety is doing. We can also look at displacement of our model as a result of those forces and fixtures. All in all, we see we have a factor of safety of about 16. This is much higher, more than 3 times as much as our desired factor of safety, so there's probably a good amount of weight to be saved on the product. And so by doing simulation in SOLIDWORKS, we're able to reduce time and money, reduce errors from hand calculations, all by doing things parametrically within the SOLIDWORKS environment. Now let's send that information over to our 3D printer. We have 2 different technologies we'll be looking at today. Fuse deposition modeling utilizes the Insight software, and PolyJet technology utilizes one called OBJET Studio. So in Insight, the first step is to bring in our STL. Any 3D modeling software is able to create the STL format, just a series of boundaries that the plastic is going to fill in. So we choose what orientation we would like it to print, and then what material we're going to use. What's going to be the layer height of that material coming down, right? So here we'll see layer by layer what it looks like as the product's built up from scratch. This shows in higher detail the rasterization between those boundaries that we mentioned. If this is going to be a structural part, we want to have a decent density. If it's just for show, then having space in between is fine. We call that a sparse fill. At that point, we go to our build stage. This is going to depend on the size of your machine. We'll choose how many of the product we'd like to print. We get great outputs like how much material we're going to be using and the time it's going to take for the print. OBJET Studio works in a very similar fashion. We start off by choosing the positioning of the part, any rotations or scaling along with it, and it too produces how much of each material we're going to be consuming, including the support. So by using digital manufacturing technologies like 3D printing, we're saving time over traditional methods like CNC or injection mold for our prototype, simplified operations because as one engineer, I'm able to handle all these processes, and again, significant cost savings from not producing those one-off parts. So now let's optimize our design. So our second one, we're taking down that shell thickness from 2.5 to just 0.5 millimeters. And through the same setup, we get results that show a factor of safety of 4, which is below our threshold of 5 that we're looking for. So it seems that we're going to have to add some material back to our model. Our third design is going to meet somewhere in the middle at 1¼ millimeters. And we see now our factor of safety is about 8.5. This is above our 5, but not too much, so I'm comfortable with this thickness. The issue now, though, is that it's not any more comfortable to hold than it was before. So let's redesign the grip to be more friendly to use. So in our fourth design, I've used the Deform tool in SOLIDWORKS to create an ergonomic grip with that same shell thickness from our last version. In order to characterize this new organic surface more accurately, we apply a mesh control in SOLIDWORKS simulation to create smaller triangles and make sure that we're capturing the real geometry. From there, we see our factor safety is about 5.6, so right above our target. I think that's pretty good to move forward. But now we need to make sure that this part can actually be injection molded. All right, so up to this point, again, we further reduced errors, stay along the theme of saving time and cost, and eliminating all those manual manufacturing and analysis steps. So let's verify the manufacturability in SOLIDWORKS plastics. We break up our solid into little pieces again to look at the flow. And we have a material library of 4,000 plus materials here, over 500 types of ABS. So we'll go through and choose our nylon again, and then look at our fill settings. So we're able to say how much time it takes for the analysis, what the melting temperatures of the material, the mold temperatures, injection pressures. These are our most fundamental parameters for setting up the analysis. Moving past the fill onto packing, we're now taking into consideration the pressure holding and pure cooling time after the plastic has filled the cavity. Finally, we need to know the ambient temperature of our factory after the part is ejected, as this will contribute to the thermal quenching stress in our warpage analysis. The last step in the setup is to define the injection locations, or the gates, for where the plastic will be entering our cavity from our sprue and runner system. We get excellent outputs like fill time, so this dynamically updates to show you how long it takes to fill up every piece of the cavity, and some just, easy gut checks to look at. So here we get a traffic light readout. Everything's green here, showing that this should be able to fill no problem, about 2/3 of the injection pressure that our machine is capable of. We're able to see the temperatures at the end of each of these phases, as well as residual stress. And both of those factor in to our warp results, which is really why at the end of the day, all of us are doing this analysis. So this plot here is showing displacement. So we have a max displacement about 0.5 millimeter. So that's pretty tight. And this is important if it's fitting against other parts, or maybe there's a snap fit in your design. A great output to have. And if that wasn't totally clear from the last image, I exaggerated here 20 times so that you can see how the product is really twisting. Right, so warp comes from non-uniform shrinkage, as well as the thermal quenching from the ejection from the mold. Right. Furthermore, we started out with our initial design, went to a rapid method of manufacturing, optimized our design, and then made sure that when we make 1,000,000 of these, that it can actually be done effectively and within tolerance. In conclusion, we've reduced our weight 40% from 47 to 28 grams. We have a more ergonomic design. We've reduced the manufacturing cycle time, and our max displacement is tolerable from our warpage. Furthermore, SOLIDWORKS with concurrent design validation and rapid prototyping is an equation for success. And remember, the 10 best tools are the ones you always have on you. Thank you for tuning in. This is David Waltzman from GoEngineer.